15.1 Definition of limits. Within this section, we are going to be going over the actual definition of what a limit is, what a limit looks like in its equation form, being able to read the equation in order to properly produce an answer, as well as looking at a graph and determining what the answer to a limit would be. In slide 2, we first begin with the understanding of what a limit will look like. Generally, you will see here in the middle, the limit of f of x is equal to L as x approaches a. Now, that's generally what a limit will look like. And this down here would be exactly how you would read your limit. Now, there are oftentimes a lot of confusion as far as, is the x approaching a over to the right-hand side? Is it underneath? Does it go before it? This is exactly what it would look like right here. So you would have the limit of f of x as x approaches a is equal to L. This can generally be broken down into 3 steps on how to read. So the limit of f of x would be step 1. As x approaches a would be step 2, equals L would be step 3. And that's exactly how it would be read. In slide 3, we go over the 4 different ways in which limits basically exist. So a limit can be a specific y value of a function. A limit can be a y value that a function gets close to. A limit can be an infinite value, and a limit does not need to exist at all. Now, I'm going to provide you different examples in which all of these occur. So a limit can be a specific y value of a function. What generally occurs here is whenever we come up to a specific answer, and that is your specific answer. For example, if it ends up being that the answer is 3, then the limit will equal that 3 number. Now, generally you will see on a line a solid dot, and you would see that be the exact location of what we are referring to. Our second example says a limit can be a y value that a function gets close to. Now, using that same example that we used for the first one, oftentimes as we have continuation throughout a line, whether it is a closed circle or whether it is an open circle, we are usually approaching from the left-hand side and we are usually approaching from the right-hand side. What we're looking at here is where those numbers are getting closer and closer to. That's why we would say that it is a value that it gets close to. The limit can be an infinite value, meaning if it continues to go up or it continues to go down, this would be an example of positive infinity or negative infinity. The last one would be a limit does not need to exist at all. There are often times where we might see a line going up to a certain point, have an open circle, have a circle once again be open further down or above, and it continue going in a different direction. In this case, our limit would not exist at all. Here we have a slide of the different areas in which limits are seen. They can be seen within a graph, numerical, they can be used within calculus, as well as you can use a analytical approach to help determine what limits are. In this example, we go over different types of limits. Here we are taking a look at our first sample problem. And it says the limit of f of x when x approaches 2 is equal to 3. Now, once again, anytime that we see that x is approaching 2 and it does not have a plus or minus sign off of the base. So if we have a 2 here, generally in this top right corner, you will either see a positive or negative sign occur there. If there is not a sign there as far as positive or negative, this means we are looking at the number from both sides, the left side and the right side. So you can see the two blue arrows that are right here. And as you can see, we are getting closer and closer to the number 2. Keep in mind, the 2 is always the x, which is what it's referring to. And wherever it is approaching, as we get closer to that 2, would be our answer as far as y. So here, our y value would be 3. In example 2, we would do the exact same thing. Now here we have x approaching 3. So as we approach 3 from the left, and as we approach 3 from the right, notice our number gets closer and closer to 4. This is the reason, once again, why x is equal to 4. Now, one thing that I do have to say about this slide in particular, or this example in particular, if we were to go over f of 3, which is specifically looking at the x value of 3, in this case, because we have an open circle, it does not exist. That is extremely important to notice, because there is a difference between approaching from left, up right, approaching from both sides, as well as just looking at the x value itself, which would, in this case would be 3. Example 3, we have an equation that says the limit of f of x as x approaches 1 is equal to 2. In this scenario, we are looking at f approaching 1, or f of 1, and this would give us an answer of 2. Our last case scenario would be example 4. Here we're given a table, and as we work our way towards that middle number, we can easily see that we're going from 0.9, 0.99, 0.999. As we get closer and closer to 1, our value on the y side of things gets closer and closer to 0.5. So in this case, for number 4, we would say the left side would approach 0.5. We take a look at the right side, 1.1, 1.01, 1.001. Notice we are getting closer to 1. And on that right-hand side, what is occurring with the y values is that we are once again getting closer to 0.5. So 0.48, 0.49, 0.499, 0.4999. In this case, this side would also go towards 0.5. Our answer here would be 0.5. Let's talk about right-sided and left-sided limits. Now, in this case, a right-sided or left-sided limit is generally a one-sided limit that is going from that specific side. So if we are looking at any type of line, and in this case, we're just going to draw this quick line here. If we are approaching from the right side, so a right-sided limit, we are going to work our way towards that exact spot. Generally, we would see this as x approaches whatever the number is, we'll call it a, and that's going to be from the plus side. The reason why it's described as a with a plus on the top right corner is very similar to a number line. So on a number line, we have 0 in the middle, we have our positive numbers on the right, negative numbers on the left. In this case, the number that we are approaching is our 0. It is our neutral number. That is the divider between the left and the right, and that's how we would describe the positive or the negative. So anytime that we are looking from the right side, it is positive. Anytime that we are looking from the left side, it would be negative. this same example approached from the left side, we would be working left to right, and we would see it as x approaching a from the left side, with a little negative sign at the top right corner of the a. In slide 7, we are here taking a look at each one of these different examples, and we're going to use our one-sided limits to help us describe exactly what is going on within this problem. So we would first start off with us taking a look at what x is approaching. In this case, we are approaching the number 2, and we are going to approach from the left side first. So we would go ahead and describe that as the limit of f of x as x approaches 2 from the negative side is equal to, we're going to go ahead and take a look at the right number. So we are approaching from this left side, and we are getting closer and closer to the number 3. And that right there would be our answer. We would also take a look at the right-hand side. So in this example, we have the limit of f of x as x approaches 2 from the positive side would be equal to, once again, the number 3. Now, as we approach a two-sided limit, this would be used any time that we have a regular number without a positive or negative. So here we would be looking at the limit of f of x as x approaches 2 is equal to 3. And we're able to do this because we're approaching from the left, we are approaching from the right, and because this line continues on the exact same line and are approaching both numbers, we're able to provide that answer. If we had a different scenario where we had an open circle and this line would continue this way, rather than here, this actually would not exist. We will do some questions in the future in order to go over these different scenarios and be able to tell the difference between them. But these are our 2 to 3 different scenarios as far as when it comes to one-sided and two-sided limits. The last approach would be if we were to run into a scenario of f of 2. Now keep in mind, f of 2, as we take a look at R2, there is an open circle there, and there are no closed circles above or below. In this case, it would not exist, or does not exist. Let's take a look at slide 8. There is a relationship between a one-sided limit and a two-sided limit. Now, a one-sided limit, we'll take a look from the one side specifically, but it is also extremely important to understand that a two-sided limit, we are still taking a look at where they are both connecting and whether or not they both hit the same spot. So let's start off with this left side. Here it says the limit of f of x as x approaches 1 is equal to 2, even though f of 1 is undefined. Remember, f of 1 is looking at the number itself. While the limit of f of x as x approaches 1 would be 2, because we're looking at a two-sided limit where we are approaching from the left and we are approaching from the right-hand side as well. Let's go ahead and take a look on the right-hand side. This one says the limit of f of x is equal to 2, even though f of 1 is equal to 4. Once again, the same thing is done again with f of 1. we are looking for a solid dot when x is equal to 1. In this case, now since we have an actual solid dot above it, f of 1 is equal to 4. Now we are still running into the limit of f of x when x approaches 1 being 2, because from the left side and the right side, we are still approaching the numerical value of 2. Let's go over this slide. Now, in this case, we have a couple different scenarios. We have x approaching 1 from the negative side. We have x approaching 1 from the positive side, and we have x approaching 1 without a sign. Let's first start off with x approaching 1 from the negative side. As we can see here, this is a one-sided limit. Notice we are following that line from the left-hand side of the 1 and getting closer and closer to that 1. As we get closer, our final value here would be 2. As we approach from the right-hand side, notice in this case, as we get closer and closer to the 1 value on the x side of things, we are getting closer and closer to -2. Our last scenario would be the approach from both the left and the right-hand side. Now, in this case, because we are ending up at x from the left side approaching 2 and x on the right side approaching -2, in this case, it would not exist because we are coming up with two values that are contrary to each other. Slide 10. Describe each point on the graph in terms of limits, then find the domain and range of the function. Let's first begin with the domain and range, because in this case, this might be a little bit easier than completing each one of our specific limits. Now, we're going to start off with our domain. So, in this case, looking left to right, notice we are starting off from 0, and we're putting a bracket with the 0 because there is a closed dot. As we work our way from left to right, notice as we hit 1, there is a closed circle at the 1, just not where the rest of the line is. So in this case, because that continues, that solid dot is there, it continues with the continuity of our graph. Same thing would occur over here at 2. It is once we get to the value of 3 where we see an open circle in which we would have to stop, use a parentheses, in union with the 3 going up to the 4. In this case, the 4 has a closed circle, which means we go ahead and place our brackets. In terms of our range, here we're looking up and down. So we begin with our lowest value, which in this case would be 1. Our highest value would be at 3. Now, as we're doing this, we keep in mind we are looking for any locations where there might be an open circle. Here at 2, we have 2 open circles, but this closed circle represents the fact that it is included within our range. So we are actually going from 1 to 3 with brackets. Now that we've tackled our domain and range, we're going to go ahead and work to write down each one of the limits that we have here, going from the left side to the right-hand side. Now, for this, we have to pay attention to where we're starting off at, understanding if there's a left side or a right side, and just working our way from there. In this case, starting with the very left-hand side, notice we cannot approach 0 from the left-hand side. There is no line there, but we can approach f of 0 to provide our answer. We can also approach the limit of f of x as x approaches 0 from the positive side to provide an answer. We go ahead and we work with our next value, which in this case would be as x approaches 1. We're going to solve all these at the very end once we have our limits all written down. Our next problem would be the limit of f of x as x approaches 1 from the negative side, the limit of f of x as x approaches 1 from the positive side, the limit of f of x as x approaches 1, and the limit, the f of 1 is equal to. We would do the same thing as x approaches 2. Limit of f of x is equal to x approaches 2 from the negative side. Limit of f of x as x approaches 2 from the positive side. Limit of f of x as x approaches 2, and f of 2. Let's go ahead and work the right side of this graph. We would continue on with 3. The limit of f of x as x approaches 3 from the negative side. The limit of f of x as x approaches 3 from the positive side. The limit of f of x as x approaches 3, and f of 3. Our last set would be the limit of f of x as x approaches 4 from the negative side. Notice we do not have it approaching from the right side, which means we do not have a 4 plus. And since we can't get both the left and the right side, we would not have a regular 4. Our last one here would be f of 4. So let's provide answers to each one of these limits that we've written down. So at f of 0, here we're looking at it directly at the 0 mark to figure out exactly what number it falls. Since we have a solid dot on the 1, this answer would be 1. The limit of f of x as x approaches 0 from the positive side. In this case, notice it is coming down to 1. The limit of f of x as x approaches 1 from the negative side. This would be 2. As it approaches from the positive side, this would also be 2. Since we are going ahead and working from the left and the right side, since they are approaching the same number, our answer here would be also 2. F of 1 would be wherever we have a solid dot on that 1 x-axis. That value would be 3. Let's take a look at 2 from the negative side. 2 from the negative side would be approaching 1. 2 from the positive side would give us 2. Now, when we're looking at the limit of f of x as x approaches 2, because we are at 2 different numbers that we are coming up to, this would actually be that it does not exist. F of 2 itself, we would look for that solid dot. In this case, our answer would be 1. On the right-hand side, we are approaching 3 from the left side. In this case, we are approaching 3. From the right side, we are also approaching 3. The left and right side are both coming to the same number, which means 3 would be our answer. Now, f of 3 does not exist because here we end up having an open circle. The limit of f of x as x approaches from the left side, that would be at 2. And f of 4 would be at 2 because we have a solid dot there. Now, in this case for slide 11, we go over a lot of the terminology that is used as well as the vocabulary in understanding the different forms of discontinuity that there is within these graphs. Many of these terms are used from previous chapters that we have gone over. So notice here we go over removable discontinuity, non-removable discontinuity, and jump discontinuity. They also go over many key definitions and understandings that you need to understand about two-sided limits. We also go over various types of notations. Here, these are different things that are used, or different notations that are used within our answers to help us have a better understanding of our answers. First one would be DNE, which means does not exist, as heard earlier within this video. We do use a positive infinity whenever the function increases without bounds, meaning it is not bounded above or below, it is not restricted, it is not within a specific range. It continues to move upward or rightward within our graph. The last would be a negative infinity whenever that function decreases without bounds. Now, in this case, for these problems, when you are given a table and you are given your function, you are generally going to have to figure out the values on the y side of your table. In this case, you would be allowed to use a calculator in order to plug in the x values into your equation to come out with a y value. So for example, on this top graph, we can see that x has 6.9, 6.99, 6.999. Keep in mind, that is occurring as well on the right side. We are approaching closer and closer to the middle number, which is 7. So it is extremely important that the numbers increase in that order. As that occurs, you can see within the y values themselves, you end up with 7.9, 7.7, 7.99, 7.999, and from the right side, 8.01, 8.001, and 8.1 on the right side. Now, as we are approaching the left and right side, notice the value itself would appear to approach 8. But because of the actual equation itself, the problem, it actually came back as undefined. This is extremely important because understanding what is going on at that middle number is extremely important in understanding, are we looking at a solid dot? Are we looking at an open circle? And vice versa. In this case, if we are looking at something that is undefined, you already know that there is going to be an open circle at that number. The same thing can occur for our bottom graph. Notice, different equation, but same scenario. Notice we are approaching from the left side with negative numbers, positive numbers from the right side to approach 0. In this case, we would generally assume that on the left side with our negative numbers, we would be approaching 0.5. On the right side, it looks like we would be approaching 0.5. But when they calculated 0, it ended up being at an error. It is more than likely that we are seeing something along this line occur, where we are going up to a number, open circle, and then that other line is coming down from it as well. In slide 14, we go over the continuity. Now here we are looking at 3 different examples of how these 3 conditions are met. So the first one says f of c is defined, a point does exist. Now generally when that does occur, you will be seeing an equation that looks something similar to f of 1 is equal to a number, for example 2. So the limit of f of x exists, there's no gap, and there's no jump in that graph. Now in order to describe something like that, we would be looking at an equation that looks similar to the limit of f of x as x approaches 1 from the negative side would be equal to 2, and the limit of f of x as x approaches 1 from the positive side would also give us 2. Notice because you're approaching from the left and the right and you're coming up to the same number, notice there is no gap, there is no jump within your table. The last one would be the limit of f of x with no hole in the graph. Now generally this can be described in one of 2 ways. This can generally be looking like a combination of both equal to each other. So the limit, so f of 1 is equal to the limit of f of x as x approaches 1 is equal to 2. So it is extremely important to understand that anytime that our lines are continuous, we are looking from negative infinity to positive infinity. If you have any questions on this slide, please feel free to email me at any point.